In this video, we're going to talk about various helpful functions for use in data science and statistics. So first, we're going to talk about some general functions that you can use in R, and then we'll talk about functions specifically related to statistical distributions before we move on to an example that you can work through yourself. So in terms of general functions, I provided a list here of various functions that I use on a regular basis. You may not use them as frequently, and there may be other functions that you would use instead. But one of the common functions I use is the length function in R, which returns the length of a vector x or a list or whatever you have. It returns the number of elements in that object. Sum of x sums the elements in a numeric vector. Mean of x provides the sample mean of the elements in x. Var of x computes the sample variance of the elements in x. St of x computes the sample standard deviation of the elements in x. Range of x provides the minimum and maximum values of elements in x. Sometimes range is used to refer to the difference between the max and the min, but when we use the range function in R, it's going to provide the minimum value and the maximum value of the elements in the object x. Log of x is by default going to return the natural logarithm of the elements in x. Summary of x is going to return a summary of x. However, you should know that this is a generic function, and so the output actually changes depending on the class of x. So the summary produced will differ depending on the kind of object x actually is. And then a function I use a ton is the str function. So str stands for structure, and it provides information about the structure of x. Usually it provides the class of the object and some information about its size. And this is really useful in practice when you're debugging code, at least for me. So I've included that in my list. As a statistician, I use a lot of functions related to statistical distributions. And so let's suppose that we have a random variable x that has the dist distribution. So there's 4 different functions that you commonly use for statistical distributions in R that start with P, Q, D, and R. So P stands for probability here, and it returns the CDF of x evaluated at a quantile Q. So this pdist function, you give it Q, the quantile, is going to return P, the probability that the random variable x is less than or equal to Q. So P stands for probability here, which is why we have pdist. Qdist, so Q stands for quantile, and so this function Qdist of P is going to return the inverse CDF or quantile function of x evaluated at P. And if you're not familiar with what a quantile function is, or an inverse CDF function is, I'm not really here to explain exactly what that is to you. That's part of a statistics course. But if you give it a probability P, then x is the quantile, the smallest value of x, such that the probability that x is less than or equal to little x is greater than or equal to this probability P. So this is the formal definition. It gets a little simpler for continuous random variables, but you don't need to know that for the purposes of this course. This is just the formal definition. So Q stands for quantile. D stands for density, and though what it actually returns depends on whether you have a continuous random variable or a discrete random variable. So Qdist of x returns the mass or density function of the random variable x evaluated at little x, depending on whether it's discrete or continuous. So if it's a discrete random variable, it returns the probability mass function, and if it's a continuous random variable, then it returns the probability density of the random variable evaluated at little x. And then lastly, you have the rdist function. So R stands for random number generation. And so essentially what rdist is going to do is it takes the argument n, which is the number of observations, and it's going to draw an IID random sample of size n from the distribution described by the random variable x. And you notice that I have ... in each one of these. And the reason for that is that most distributions have a number of parameters that you have to specify. And so that ... here indicates that you're probably going to have to give a few more arguments to the function to get it to work. But in general, P stands for probability or CDF of a random variable. Q stands for quantile. D stands for density of a random variable. And R stands for random number generation. So Let's do an example where we actually apply these in practice. So I want you to execute the following commands in R to see this output. So you can just copy and paste that into your R console. So I've already done that in RStudio, but we're going to look at a P function here, a Q function, a D function, another D function, generate some random variables, and then we want to run the last command, this one right here, assign it the name x, and then apply all of the general functions, the functions up here, to the vector that we've assigned. So let's head over to RStudio and see what we get here. So P norm, so this is going to be the CDF of a normal distribution. We want to evaluate it at the quantile 1.96, and we want to do this for a normal distribution with a mean of 0 and a standard deviation of 1, meaning it's a standard normal. And so this should be something like 0.975. If you have constructed confidence intervals for normal distribution, then you've probably seen this number come up before. So Q uniform of 0.6. So we want the quantile of a uniform distribution running from a minimum value of 0 up to a maximum value of 1. And if you know anything about the uniform distribution, it means that each value is equally likely. So in fact, the quantile for a probability of 0.6 is going to be 0.6. And this is specific for a uniform distribution. That wasn't something you were expecting. That's not a problem for this course. That's something for a statistical course, but that is the quantile returned by R. D binom. So a binomial distribution is a discrete random variable that depends on a fixed number of trials, which in this case is 20, and a probability of success, which in this case we're saying is equal to 0.2. And so we want to compute the probability that our random variable, our binomial random variable, takes the value 2 when we have 20 trials and the probability of success is equal to 0.2. So we run that using Control Enter on my PC here, and we get about 0.14. So the probability that we get 2 successes out of 20 trials is about 14% for this particular distribution. Now we're going to use dexp. So exp here stands for the exponential distribution. And we want to evaluate the density function for an exponential distribution with a rate equal to 2. And so if you weren't sure exactly what that meant, of course you could use the question mark dexp to get more information about the exponential distribution here. And so this has a bunch of information, but the key detail here is that we have the rate parameter here. What it says here is that for an exponential distribution, the rate has a relationship that the mean is equal to 1 over rate. So if you know the mean of your exponential distribution, the rate is going to be the reciprocal of that. So I want to evaluate the density function of the exponential distribution at 1, assuming the exponential distribution has a rate of 2, which means a mean of 1/2. And so when we do that, we get a density of 0.27. And then lastly here I have R chi-squared. So this is going to generate 100 values from a chi-square distribution with 5 degrees of freedom. Okay, so I have 100 values there. This may not mean anything to you, but we're sampling IID. We are drawing an IID sample from a chi-square distribution with 5 degrees of freedom. And if you want to learn more about the available distributions in R, you can type distributions, and it brings up a number of distributions that are available in R by default. And there are other ones and packages and things like that, but these are the main functions, the main statistical distributions that are available in R automatically. And so as I said, the last thing we wanted to do here was we wanted to take 100 values from this chi-square distribution with 5 degrees of freedom. We wanted to assign it the name x, so I can look at what that is here. So a bunch of values. And then I wanted to use these different functions, these different general functions on x. So I drew 100 values from my chi-square distribution, so the length should equal 100. I have no idea what the sum is going to be here. Okay, it says 506. If we look at the mean of x, it should be about 5. And then the variance should be 2 times that. So 11, so a little bit more than that. Usually there's more variability in an estimate of a variance. The standard deviation then is going to be the square root of 11.73 here. So we get 3.426. The range of values, so it's going to give us the minimum value and the maximum value. So in my example, I get 0.45 up to 20.15. You may get something different in yours because you'll be drawing different values from your random number generator. We do a summary of x, we should actually get a 6-number summary. So you can see we have the minimum value, the 0.25 quantile, the median value, the mean value, the 0.75 quantile, and then the maximum value of that vector x. And then lastly, I look at the structure of x, and we see here that it is a numeric vector with 100 different values in it.